So in this section, we're going to look at some trends on the periodic table. And the first one we're going to look at is atomic radius. So here it's showing us that the atomic radius here is defined as the distance between the two nuclei. And actually there are several definitions of atomic radius, such as van der Waals radius and others. But here we're just going to basically look at a trend in the atomic radius. So again, here's one way of looking at it, the distance between the two nuclei. So if you notice, for fluorine, the two nuclei are closer together than for iodine, which is shown here. And that's because iodine is a bigger molecule than fluorine. So the electron clouds are bigger, so therefore the nuclei are further away. One way of thinking about this is, as you move down a group on the periodic table, you're adding more ends, right? More layers of electrons, or more principal quantum numbers. And when you do this, this causes the atoms to be bigger. There's also another general trend, which is that as you move this way across the periodic table, the atoms get bigger. And that is a little bit less clear because if you look at the mass increases in this direction. But if you look at the radius increases in this direction. And one reason for that is something called the effective nuclear charge. So let's look at two different elements. I'm not going to spend a lot of time on effective nuclear charge, but I just want to explain what it is. The first one we're going to look at is lithium. So lithium is 3 plus. It has 3 protons. It's not lithium 3 plus. Lithium has 3 protons in its nucleus. So let me redraw this. Let me just try again. So let's look at lithium, which has a 3 plus charge in its nucleus, and this is lithium. So the reason it has a 3 plus charge is its atomic number is 3. It's got 3 protons. Well, it has 2 electrons in n equals 1 and 1 electron in n equals 2. That's its electron configuration, 1s2, 2s2. If we contrast that with the other end, which is fluorine, or neon, I'm going to use fluorine here. Fluorine has a plus 9 charge because it has 9 protons. It has 2 electrons in n equals 1. And it has 7, 1, 2, 3, 4, 5, 6, 7 electrons in n equals 2. Said another way, it has 7 valence electrons. Remember that the valence electrons is equal to the A group number. So lithium has 1 valence electron and fluorine has 7 valence electrons. The way that this is thought of is that these inner electrons shield the positive charge in the nucleus. So essentially, this electron feels a plus 1 charge. This is called the effective nuclear charge, and it's sometimes written as Z effective. And for main group elements, it's equal to the valence, the number of valence electrons, which are the outermost electrons, which you'll recall is the A group number. So 1A has 1 valence, 2A has 2, 3A has 3, 4A has 4. That's how many valence electrons they have. It is also their effective nuclear charge. So this basically is feeling a plus 1 charge. Let's look over here. Well, here you have these 2 electrons shielding 2 of these protons. So these outer electrons feel a plus 7 charge, or Z effective is plus 7, which is equal to the number of valence electrons for the main group elements. So the idea is basically here, these electrons are feeling a plus 7 charge, so they can be pulled in more than these electrons that are only feeling a plus 1 charge. They have more freedom. This electron, it has more freedom because it only feels a plus 1 charge. Since opposites attract, the positive charge the more the positive charge, the greater it can pull in that electron density. And that is basically what we have going on here, which leads us to a trend on the periodic table, which is, generally speaking, that atomic radius increases down and to the left. And that is a general trend. Now, I do need to show you one other thing. If you look at the transition elements, they're kind of weird. And they kind of tend to be big on the ends and smaller in the middle. And they have this kind of dipping feeling. So this is radius versus atomic number. So the trend for main groups is clear. Lithium is the largest, and neon is the smallest in its group. Potassium to krypton, same thing. But the transition elements have this weird U-shaped thing. You don't really need to know that here. You're not going to be asked that, but it is worth pointing out. And again, we get to this general trend of increasing atomic radius as we go down and to the left. So essentially what we can think of, if we look at a periodic table, is cesium is the biggest, and helium is the smallest. And as we go down and across, they get larger and larger and larger. So let's look at a question you might be asked. Well, the question is, rank the following in order of decreasing atomic radius. So the first thing we need to do is we need to find these elements on the periodic table, and I'm going to use this one just to show relatively where these elements are on your periodic table. So first we have rubidium. First we have chlorine, and chlorine is somewhere here in 7A. Then we have rubidium. Rubidium's pretty far down in 1A. And then finally sodium, which is in 1A, but it's in the same period as chlorine. That is period 3. So these are our three elements. Sodium and chlorine are in the same period, and rubidium is down here. Now, in these chapters, you're going to do a lot of ranking. So when it says rank in order of decreasing atomic radius, decreasing order means biggest first. And I suggest making that translation so that you don't do it backwards. So always ask yourself, does it want biggest first or does it want smallest first? Well, if it's decreasing order, if they get smaller as it goes, you want the biggest one first. If it's increasing order, like in the next case, you want the smallest first. Back to our job. We want to find which of these is the biggest. Well, which one's closest to the bottom left-hand corner? That is rubidium, which is greater than sodium, which is greater than chlorine, which is closest to the upper right-hand corner. So this is the order of the atoms. I'm just going to switch these so I can rewrite the relative ions or atoms and the second one. So it says rank the following in terms of increasing atomic radius. So here we have an increasing atomic radius. And it's the same exact idea, except this time we want it in the opposite order. So the first thing we want to do is find these things. Well, fluorine is about here. Bromine is about here, relatively speaking. And potassium is in period 4, just like bromine, except it's all the way over here. Now it says, rank them in terms of increasing atomic radius. So if it's increasing, you want them to get bigger, you want to put the smallest, as we mentioned before, first. So we want to put the smallest first. Well, which one's closest to the upper right-hand corner? Fluorine is less than bromine, because it's way over to the right, is less than potassium, because it's closer to the left. So these are the orders of increasing and decreasing atomic radius. The next thing we want to look at is ionic radius, which follows a different trend. It's not really a trend. Basically, what we have for ionic radius is that when things become positively charged, they get smaller. When they become negatively charged, they get larger. And what you can think about this is sulfur and sulfur 2- both have 16 protons. In the case of sulfur, those 16 protons are pulling on 16 electrons. In the case of sulfur 2 minus, those 16 protons are pulling on 18 electrons. They can't as effectively pull on 18 electrons, so the size is larger. The electrons are further away from the nucleus. In the positive case, you can think of it two different ways. In the case of aluminum going to aluminum 3 plus, it actually loses all of its electrons in n equals 3. So it has one less shell, so it gets smaller. Or another way of thinking about it is that if in neutral aluminum there's 13 protons pulling on 13 electrons, in aluminum 3 plus there's 13 protons pulling on 10 electrons, so it can pull them in much smaller. So you can see here this is what happens with ionic radius, and the general rule is positive ions get smaller, same protons but less electrons. Negative ions get bigger, same protons, but more electrons. Because ions always have the same number of protons as the atom they came from, what changes is the number of electrons, and that's what leads us to this general rule. So let's look at an example here. Let's say we had this series of atoms slash ions. We have oxygen 2 minus, F minus, neon, sodium plus, and Mg2 plus. And if we look at the periodic table and we find these things, this is O2 minus, F minus, neon, Na plus, and Mg2 plus. And if we were to draw the electron configuration of any of these things, we would find that they are 1s2, there should be a 2 in there, 2s2, 2p6. So again, 1s2, 2s2, 2p6. So these are the electron configuration. This is the electron configuration of all of these. Said another way, these all have the same electron configuration. But let's look at the number of protons. O2 minus has 8, F minus has 9, neon has 10, sodium has 11, and magnesium 2 plus has 12. So if we look at this, they have the same number of electrons and the same electron configuration, but they have different numbers of protons. So here it says, rank the ions above in terms of increasing radius. Remember that increasing means smallest first. Well, which one's going to be the smallest? Well, if they all have the same number of electrons, the one with the most protons is going to be the smallest because it's going to pull those electrons closer to the nucleus. Or if you remember the general trend before, more protons makes atoms smaller, and less protons makes them bigger. Or said another way, positive ions get smaller and negative ions get bigger. So what do we want to do for the smallest first? Well, the smallest here is Mg2 plus, which is less than Na plus, which is less than neon, which is less than F minus, which is less than O2 minus. So we're really ranking them in terms of the number of protons they have. The more protons, the smaller they are. And this is for isoelectronic species. So next we want to shift gears a little bit and look at a whole different trend. And that trend is ionization energy. So we're going to look at two trends in the final part of this chapter, and they are ionization energy and electron affinity. And they're exact opposites of each other. Ionization energy is the energy required to take away an electron. So starting with M in the gas phase, we get M plus in the gas phase plus an electron. That's the first ionization energy. We could take away another electron. The second ionization energy is M plus in the gas phase, so we start with the product of the first ionization energy. We take away another electron and we get M2 plus in the gas phase plus an electron. We could have a third ionization energy, so we start with the product of the second ionization energy, and we have M2 plus in the gas phase yields M3 plus in the gas phase plus an electron. So ionization energy is the energy to take away an electron. So ionization energy is the energy to take away an electron. Now there's a couple of things to note. One, we could in theory have ionization energies until all the electrons were gone. I should note that it would take massive amounts of energy in order to take away, like 40 electrons from something. So it's not practically possible, but it is theoretically possible. The other takeaway for ionization energies is that the element, here we have M, which is just any element, has to be in the gas phase. So it's the energy to take an electron away from the element in the gas phase. The ion that you get is also in the gas phase. So it says, what is the chemical equation for the first ionization energy of carbon? So if we look at the first ionization energy of carbon, it's going to be carbon, has to be in the gas phase, yields carbon plus in the gas phase plus an electron. It says, what is the chemical equation for the third ionization energy of aluminum? Well, if it's the third ionization energy, aluminum must have already lost 2 electrons, so it's aluminum 2 plus in the gas phase, yields aluminum 3 plus in the gas phase plus an electron. So here we have the third ionization energy. In the next questions, we're asked to rank these in terms of ionization energy. And these are first ionization energies. So what we're looking at here is this general trend. It's hardest to take an electron away from helium, a noble gas that is extremely unreactive, and easiest to take an electron away from cesium, a 1A metal that practically wants to give that electron away. So this is the general trend. You'll note that this is exactly the opposite of the general trend of the the atomic radius. So this is the trend for ionization energy. So it says rank the following in order of decreasing first ionization energy. So decreasing means biggest first. So we want to put the biggest one first. So we need to find these atoms on the periodic table, and I'm going to use this one up here, and then we can do this. So carbon, somewhere about here, silicon's directly below it, and I should say this is not drawn to scale. These are probably a little smaller than the boxes should be. And oxygen, and it's probably more like here, but it doesn't matter because it's relative. Oxygen is about here. So we want the order, rank the following in order of decreasing first ionization energy. So decreasing first ionization energy, again, means biggest first. So oxygen is the biggest, it's closest to helium, followed by carbon, followed by silicon. So those are your ionization energies. I have another one of these to do the other one. We have rank the following in terms of increasing first ionization energy. So increasing means smallest first. Now I need to find the smallest one. Well, I need to find the atoms on the periodic table. So starting with cesium's about here, potassium's about here, and krypton is in the same period as potassium. It's just the noble gas. So now I want the one with the smallest first ionization energy first, the closest to the bottom left-hand corner. So cesium is less than potassium, is less than krypton. So this is the way that we can order things in terms of their first ionization energy. Another way first ionization energy or ionization energy in general can be asked is in terms of successive ionization energies. And here what we're looking for is a drastic change in the trend. So look here. The first ionization energy of sodium is 4,000, or excuse me, it's 400, because you're taking away a valence electron. As soon as you take away a core electron, or you take an electron away from something with the same electron configuration as a noble gas, it jumps up by 10 times. For magnesium, the first two electrons are valence electrons. Let me say that again. For magnesium, the first two electrons are valence electrons. So about 700, about 1400. Then it jumps up to about 7000 when you take an electron away from something that's noble gas-like, or you take away a core electron. For aluminum, about 600, about 1800, about 2700. Then it jumps up to 11,000 because you're taking away a core electron. So when you see this large jump, you are basically taking away a core electron. So here it says, what period 2 element is described by the following ionization energies? And what we have is IE1, 725, IE2, 1410, IE3, 8520. So we see that it has 2 core electrons, because this is about double of this. Of course, it takes more energy to take away the second electron, because after the first one goes away, the period 2 element is positively charged. So you have to add more energy to take away a second electron. But then to take away a third electron takes a massive amount of energy. So this period 2 element must have 2 valence electrons. So if we look at the periodic table, which period 2 element has 2 valence electrons? Well, that's beryllium. Takes a little bit of energy to take away the first electron. It takes a little bit more energy to take away the second electron. Then it's like helium. To take away that third electron takes a massive amount of energy. So this is the first electron, this is the second electron, then it's like helium, so it takes a massive amount of energy to take away the third electron. So you go from 1410 up to 8520. And these numbers are made up, so they're not exactly the correct numbers, but the general trend is there. So this is the way that successive ionization energies can be looked at here. The last thing that we want to talk about in this chapter is electron affinity. And electron affinity is the exact opposite of ionization energy. So in the case of ionization energy, that's the energy to take an electron away. In the case of electron affinity, it's the energy to add an electron. So here we have M, any atom, in the gas phase plus an electron yields M minus in the gas phase. We have M minus in the gas phase plus an electron yields M2 minus in the gas phase. And M2 minus in the gas phase plus an electron yields M3 minus in the gas phase. So this is the electron affinity 1, electron affinity 2, and that should say electron affinity 3. So these are the successive electron affinities. Now, what's important to note is this is exactly the opposite of the ionization energy. So this is the energy required to take the electron away. So it says, what is the chemical equation for the first electron affinity of carbon? So this is the energy to take the first electron away from carbon. Carbon has to be in the gas phase, just like for ionization energy. And we're going to give it an electron. And when we give carbon an electron, it's carbon minus in the gas phase. Remember, for ionization energy, we were taking an electron away. For electron affinity, we are adding an electron. It says, what is the chemical equation for the second electron affinity of sulfur? Well, sulfur already has an electron, if it's the second electron affinity, so it's already S minus. We add another electron, and it becomes S2 minus. Now, you'll recall that for ionization energy, where everything also had to be in the gas phase, there was a general trend. If we look at the trend for electron affinities, it's not quite so clear. So for example, as we go down, for whatever reason, neon has a -1. As we go across in this direction, there's no clear trend. Beryllium and these 2A1s are plus 240, plus 230. These are all in kilojoules per mole. So this is the energy required to give something an electron. And in some cases, it's negative, so it's exothermic. You give fluorine an electron and energy is released. In the case of beryllium, you have to actually put energy in to get it to take an electron. So these are no real clear trend in electron affinity, so therefore you're not going to get one of these boxes with an arrow in it for the electron affinity. But you're still responsible for knowing that electron affinity is the energy that's consumed or released to give something an electron. That something has to be in the gas phase, and its charge is negative after it takes that electron. So these have been some trends on the periodic table, as well as learning what ionization energy and electron affinity are.